Today I want to talk with you about my approach, foundation model approach, generating point clouds for Scan-to-BIM training and BIM model generation. The work is carried out by me, Nils Sören Krause, and my professorship like Joern Ploennig. Thanks for being welcome here in Portugal. And hopefully you will find the insights and the results like interesting, or we can discuss about it after the presentation. So let's start with the motivation about it. On the right side with the picture, it's like a data set from a real scan point cloud, and I think everybody of you needs to say, okay, it's a lot of effort to require or segment and label point cloud data out of real data scans. The Scan-to-BIM methods for me was the motivation of it. Okay, I don't want to segment and label all the data by manual effort, and the effort is increasing because we want to use like AI and we want to use like machine learning methods for do the process. The data, if it's labeled, we can use it fast. And if it's not labeled, we need to do it. So afterwards, the last point is like the synthetic point clouds can offer more scalability that we think, but they were like limited in their variation of these. So we have one object and we can't verify the point cloud object to like it's bigger, it's something like different. And what is the problem on it? The problem is like the labeling requires a lot of manual effort, it's time-intensive work, and we need it for the AI methods. So, and each training data or each object we want to train to the model needs a different data set to train it. And the way to do it for me wasn't like, okay, let's turn into synthetic data sets for point clouds, and let's generate it like parameterizable objects through like foundation models like ChatGPT-4, or you can use same models like DeepSeek, Gemini, what you want, if you can go through the API to the model. So the idea is, in that paper we used the model like GPT-4o for the data generation. There's no classical CIB modeling or something into the paper. We go like a pipeline from text to code to the point clouds, and the approach is like it's a modular approach because the objects are parameterizable and adaptable to other objects, probably over the foundation models to generate new code, and it's a non-black box approach. So, and the data set afterwards is fully synthetic. If you don't want to have a fully synthetic data set, you can implement like real data scanned from the BLK2Go or Leica, and you can get the noise from them and sample the noise to the synthetic data set. So if you need the noise for like prediction and training the models afterwards. What did we do in that paper? It's the next question. We do like complexity tests. What can we generate with the foundation model? Afterwards, we generated point clouds from like floor plan images. Then we going a little bit deeper into one object, and we show how this parameterizable object in form of a point cloud is working. So let's dive shortly to the method. The first thing is, okay, we getting the text-based information from the space or from the rooms. So everybody knows we can say a room had a height like 2 meters, a breadth like 4 meters, and a length like 5 meters or something like that. And then we're going to analyze these options with like a model over an API or over like the prompting channel of the model, and generate the code for like a point cloud of the room. So we can use it afterwards, and the model knows, okay, this information is getting in and this information is getting out first. If that is not working directly, we need to implement like a loop or something like that to stay clear. And if it's work, we can go down. So we go to the code to cloud form, after the analysis of the data with the model and the generation. And for the end, if it's worked, we can store it and we can label it. The labeling is like, in that approach, it's an automated system, so it's automated into the code. You will see it afterwards in the object I show you. And then, if it fails, we need to optimize the code. That's normal if you program something or something, you need to optimize it if it's not working. That's a load back at the end of it. It's an easy approach, but it works, and let's see how you find it. Then we're going to dive into the results shortly. The first result was like the complexity test. I called it like the complexity test generation 1. For that, we generated like really simple geometric objects. But that geometric objects are like everywhere. So if we look into the room here, we have like rectangles, we have like cubics, we have like cylinders, we have like cones or prisms and pyramids, not more or not less. And we worked it out firstly for the sphere. On the left side, for the cylinder that works, for the cube that works, for cubit it works, and for the cone it works as well. If we're going to look like on the prism side, there was some problems in the pyramid. This was not working as well. So probably if we go later to other objects, let's see if the roofs are working for the buildings or not. The next test was, okay, the complexity of generation 2. It's called like this because we started with like an easy object. We started with like a rectangle object. Afterwards, we go to take the rectangle objects and expand it to like 4 rooms into one space. And afterwards, we're going to take like the first space into a second space upwards. Then we go into like objects. We prompted the model with like the prompt of, okay, put walls or put like windows into the walls. And that worked as well, but the showing of it is a little bit different. It's not a real window or something like that. It's only like the positioning. And we can say, okay, the model knows they have to position like windows into the outer walls of the building. And then we're going to test like, okay, we need a roof for the building. We need like outer walls for the building if we get a complete scan out of it. And first we got on the top of the building, like it's the red points of it, that's the roof. In the first step, we have down the black points, that's the outer wall of the geometry, and the yellow points are the inner walls of the geometry. Then we adapted, okay, can we take the roof better? Because it's not a roof if we have like a rectangle about the object. So, but the model was not able to get the pyramid or the form of the roof like a really correct form for the building. So it was, yeah, we need to go to the code and take it to the other side. The last result of it was like, okay, then we need to check how we can get like more data from it. So we need to change the directions of, can you say, okay, there are different room types, there are different roof types or something like that. And this was the result of, okay, it was not working to stay the model, go to change the directions of the model and say, take like round rooms or something like that, that not works. The last result of it is like, okay, we have a little building and we have like with foundations, we have outer walls, we have inner walls, and we have the roof, and we have like a little balcony. And that point cloud is like created directly as synthetic data from like the foundation model. So then let's go to the floor plans. I think it's another interesting approach. We tested it not with real floor plans. That's like the next step or something like that, because you can get some semantic information from the floor plans and implement it as well to the models. But let's see how it works like this. So we instructed to analyze the generated image and create like a synthetic point cloud of it. Yes?
Yeah, hurry up.
It's okay.
We use a couple of minutes, so we reduce the other.
Yeah, it's okay. And so we generated the image, then we generated out of the image like the point cloud. It's like a point cloud in cloud comparing, something like that. But the problem was we have no height. So the point cloud is like a 2D projection of the picture, and it's useless to analyze it or train models with it. So we can do like edge detection or something like that, but it's useless. Next step was, okay, generating the floor plan with like the code snippets we got before from the walls. So we prompted like the new code snippets into the model, and we checked out of it to generate like more floor plans or direct changing rooms. So, and that was the result. So we have some different shapes of forms into that floor plan. We have a height. We can say the model, okay, we have the outer wall, we have the inner wall, and the connection between the walls are given from the model directly. So we only need to like implement like doors or windows to get a complete full building, and afterwards we can label it, and we can use it like training data for like other methods. The last was, okay, a little bit deeper into one object of the point cloud. It's like we generated a window for like, okay, show how the generation of one object is working. And in red you can see like the outer window frame, and the blue you can see like the window pane. It's like a synthetic object, and it's not a real window. So in a real scan you will not have the window pane because of the reflections or something like that. But for the comparison and to show how it works, and if it works really, we need to compare like, okay, the cloud direct to a normal object modeled from a BIM model, and we formed that object down again to the cloud. We took the mesh from the object, we put points into the mesh of the object, and then we compared the distances between the points. So the comparison was like this. We did it in cloud compare. In blue we have like the window frame, and in green we have like the window frame. And we can see that the distances from the object are predominantly between like 0 and 7 millimeters for the window frame. And for the window pane, we have like the objects deviations from 1.5 centimeters to 2 centimeters. And I think that's okay for like training data for models, because if we go into the reality of it, we go to window and we go to measure the opening of the window, something like in the construction site, we don't like deviations between one millimeter or something like that. So that was the object, and in further work, I think we will do some other objects that will be parameterizable, and the parameterizability of the object is like the height and the depth and the brightness of the object. So let's discuss it a little bit. The problem was afterwards, okay, if we're going to generate like...
Try to be very short
Yeah.
here. Don't do the company that, otherwise
Okay.
we have no time for...
So really short, then we go...
Literally in one sentence?
Yeah, I go through it. So we go for the outlook. We have like scalable data now. We can generate a lot of different point cloud objects, and we can extend the approach to like other approaches. So thanks for listening, and let's have a discussion about it.